All right, in order to do well in chapter 10, where we're looking at properties of liquids and solids, which are based on intermolecular forces, we really need to remember Lewis structures. So I'm just going to do a quick review of Lewis structures and focus on what is particularly important for Chem 112, which is not the same as what you learned in 111. So we're going to kind of narrow it down to that. You need to remember your structures, particularly this group, and we're only looking up to 4 electron pairs or 4 electron groups. We're not going to really worry about incomplete or expanded octets in Chem 112. They're not really very common. Most compounds in nature and real life, even in the lab, are carbon based, and they always stop at 4. So we're just going to look at those instead. Everything that we do in terms of chemistry is going to be start out by based on what the structure of the molecule looks like. So when we do this, we've got to remember a couple of things. So let's go to some sort of simple Lewis structures. Hints, and again, focusing on what's important for Chem 112. First of all, we need to remember that we can figure out what had good formal charges. So if you don't remember a formal charge from Chem 111, formal charge is just a methodology that we use to get a nice stable structure. So for example, quick note, we could draw carbon dioxide and may use dots for bonds. I'm only going to use it probably for this case. If we draw carbon dioxide, by the way, carbon dioxide has 16 electrons. Remember, when we do this, we're going to step 1, count valence electrons. Remember, the valence electron is the group that it's in, and that would be like groups 1 through 8, ignoring those transition metal groups. We're going to count those up total. That's going to be our budget for the molecule. Remember, we're going to put the element with the lowest electronegativity in the center. And remember, the highest electronegativity is fluorine, and it decreases as we go to the left and down. So carbon is going to have a lower electronegativity than oxygen, oxygen being closer to fluorine. All right, we know that we are going to need to obey the octet rule. The only element in Chem 111, or excuse me, Chem 112 that doesn't, quote, obey the octet rule is hydrogen, only because hydrogen is never going to have total of 8 electrons. It's always going to stop at 2. It's the nearest full noble gas core that we want with our elements. So obey the octet rule with a note, except hydrogen, which is going to have 1 bond only. All right, so if we take a look and we do our carbon dioxide and we count this up, if we've got CO2, we've got 4 electrons on carbon, we've got 2 oxygens, we've got 6 electrons each, and that's going to give us 16 valence electrons. If we started and we just drew this structure out, we would take and we would bond our carbon to our oxygens. After we do this, we put our remaining electrons on the outside. And if we did that, we would put our remaining electrons in order to get our total of 16 on our oxygens outside first. Remember, the only exception is hydrogen, 1 bond only. When we do this, this gives us 16 electrons, but the octet rule is not obeyed for carbon. This only has 4. It needs 8, so we're just going to take and we're going to bring some pairs in. And when we do this and we bring our pairs in, we're going to get the structure right here. We love the symmetry on this one. It gives us nice even on both sides, but with the note, this is also the correct structure of carbon dioxide, and this also has 0 formal charges. And this has a 0 formal charge for each of these elements. Now, 0 formal charge means we've got the best possible electron distribution. Formal charge, I'm going to shorthand it as an FC. Our formal charge, by definition, here is equal to valence minus ons. And you're simply going to do this for each element. And when we do this for each element, the valence is the number it brings in. So in this case, if we take and we start, let's say, with carbon, it brings in 4 electrons and minus what it owns. So we need to define what it owns. It owns half the electrons in bonds and all its lone pairs. So if we look at carbon and we try to figure out what it owns half of its electrons in bonds. And the easiest thing to do is simply split the bonds in half. And then you just count dots, because that's automatically going to be half the electrons in its bonds, and it's going to shift over its lone pairs. So if we look at this and we look at carbon, it has 4 valence electrons. It owns in this, it's got 4 in its little side. So it's going to be 4 minus 4, and it's going to have a 0 formal charge. If we do oxygen, oxygen brings in 6. It owns 1/2 of the electrons in bonds. Please note we have double bonds, which means that we have 4 electrons. If we divide that by 2, that's going to be 2. And then we look at how many lone pairs it has. It has 2 lone pairs for another 4 electrons. So if we look at this, it has a total of 6 that it owns for a 0 formal charge. Now, why do we care? Because this is not the only possible electron distribution for carbon dioxide. We also have a really bad possible electron distribution, and that would be if we started out with our carbon, with our single bonds to our oxygen. Again, recognizing that this does not obey the octet rule, and we start shifting electrons in. Now, the only thing was obey the octet rule. So if I did that, I could actually take and bring in all 3 lone pairs from 2 lone pairs from one of the oxygens and just leave 1 lone pair back. If I did this, I would get carbon, and now it would have a triple bond to one of the oxygens. It's on the right side here. And a single bond to the other oxygen, leaving the rest of the lone pairs where they are, and we could calculate the formal charge on this one as well. When we do this and we do valence minus owns, carbon has 4 valence electrons. It owns 4 in this structure with a 0 formal charge. The oxygen on the right has 6 valence electrons. It owns 7 in this structure with a -1 formal charge. It owns, in a sense, in this structure, 1 more electron than it did in that nice double bonded structure. The oxygen on the left is electron deficient. It brought in 6, but it only owns 5 in this structure, giving it a formal charge of +1. Elements or molecules are more stable when all of the formal charges are as close to 0 as possible. So this triple bonded structure for carbon dioxide does not exist. Okay, it's a bad distribution of electrons, even though we can draw it and it follows the octet rule. We're not going to use that one. We're not going to use this one because the electron distribution does not give us a stable structure, so it doesn't exist. Why do we care? Because we've got some really simple ways to figure out what are good structures with good formal charges. And these are the rules. We're going to start out here with carbon, and then we're going to consider nitrogen, we're going to consider oxygen, and we're going to consider group 7. And what we're doing is looking at possibilities with a 0 formal charge. 0 formal charges is going to give us nice stable structures. In the case of carbon, it has 4 bonds and 0 lone pairs. Nitrogen has 3 bonds and 1 lone pair. Oxygen has 2 bonds and 2 lone pairs. If I go to group 7 is going to have 1 bond and 3 lone pairs. These are going to give us really nice stable structure. These are going to obey the octet rule, and with the note, hydrogen always has 1 bond. All right, so how does that help us? Well, we don't even have to do any thinking with carbon dioxide now. We know carbon wants 4 bonds. So if carbon wants 4 bonds, we're going to double bond to each oxygen. Oxygen wants 2 bonds and 2 lone pairs. It has 2 bonds and 2 lone pairs. Kind of end of discussion. When we go to organic structures, and when we have organic structures, please note that carbon is going to do it in multiple forms. There's only over 50 million known organic compounds. And when we look at these, carbon makes chains and rings. And we need to consider these. It's going to do that such it has 4 bonds on the carbon. And when we write these out, we've got a couple of ways of doing this. We have, and I'm just going to start out with propane, with this structure here. If we have a CH3, remembering that carbon wants 4 bonds, hydrogen wants 1, and this would tell us that what we have with our CH3 is our carbon, the hydrogens, 3 hydrogens, and it's going to have to bond to something else. If we have a CH2, CH2 means it's going to bond to 2 other things. And with my CH3s, I can have the on either end. So if I think about this, and my CH3 is on the end, CH2 is going to be in the middle somewhere, bonded to 2 different things. So with that in mind, if I go back to my first page here, and I do C3H6, and the first thing, of course, I'm going to do is change that, C3H8. Okay, what do we do with this thing? All right, well, we know carbon makes chains, so we're going to chain our carbon. Let's put on 8 hydrogens. If we put on 8 hydrogens, we know we're going to have 4 bonds on the carbon. The chain to the other carbon is 1 to each hydrogen, and then I'm going to keep going. CH2 in the middle is going to have the 2 bonds to the carbons and the 2 bonds to the hydrogens. And when I take and I finish there, I am looking at C3H8. I could also write that as CH3, CH2, CH3, just different forms of the same structure. Now, what are we going to do with this? We need to figure out the geometries. So when we figure out the geometries, please remember that what we're going to have here are we're going to obey the octet rule, which means we're really only going to care about these few options. And so what we look at are the number of things attached. In the case of all of those carbons, I have 4 things attached. Remember on that first carbon here, I have 3 hydrogens and a carbon. Second carbon, 2 carbons and 2 hydrogens, and that's going to give me 4 attached. And what I have, because all 4 are attached and no lone pairs, is I have tetrahedral on each carbon. With a note, and this is really, really important, hydrocarbons are nonpolar. If your compound contains hydrogen and carbon only, it is inherently nonpolar. There is not a big enough difference between the electronegativity of hydrogen and carbon to give us polarity. So note, hydrocarbons are nonpolar. All right, let's go to the next one. And let's do this guy down here. CH3, CH2, CH2, NH2, and you go, but then you go, oh, well, I know CH3 means it's on the outside. I know CH2 means it's in the middle. I've got another CH2 in the middle, and then I have an NH2. Well, we know that nitrogen wants to have 3 bonds and a lone pair. And when we do this, we could add up all of our electrons, and if we added up all of our electrons, we would get precisely this. Because when we have our nice clean structures here, unless we've got a positive or a negative, we're going to obey the octet rule on pretty much anything organic, and we're going to have a nice clean structure. The 3 carbons here are all tetrahedral. But with the case of this nitrogen on the end, it is not tetrahedral. We need to consider its geometry. It is attached to these things here. It is attached to a carbon, 2 hydrogens, and it has a lone pair. If we take and we go back and look at our structures, we are now right here. If we are right here, the geometry on that nitrogen is trigonal pyramidal. And the key on this is that we're going to go into something now that becomes polar. So we need to understand what is going to be polar. What is going to be polar is any of our structures here that have lone pairs. These are polar always. Anytime you have a lone pair, it is going to give you polarity, end of discussion. The other time we're going to have polarity is if we have two different elements attached to our central atom. And it doesn't matter which one of these we have, if we have two different elements attached, we are going to have polarity. And all we need to do to have polarity is we need to have a difference on the two different sides of our atom. So if we have two different things attached, these would be polar. If we have the same attached, so if I had one of these where everything was the same, this would be nonpolar. Anytime you have two or more different elements, different atoms on the central, or lone pair on the central, it is going to be polar. And that's it. That's all you need to know for polarity. So if we look at this guy, it's got a lone pair on the nitrogen, and this thing is going to be polar. This one here is tetrahedral on each carbon. It's a hydrocarbon. All hydrocarbons are nonpolar. If we do this last one here of our NH2 CO2H, and we again start to overthink it, and then we stop and we remember our rules. We know that nitrogen wants to have 3 bonds and a lone pair. We know that here both atoms are attached to the carbon. So we're going to put a carbon, or excuse me, both oxygens, oxygen and an oxygen. But we know that carbon wants to have 2 bonds, a double bond. So I'm going to double bond to the top one, not for any good reason, except that I've run out of space. I know my other oxygen likes to have 2 bonds as well. Hydrogen wants 1. So I'm going to take and I'm going to do that and fill in my electrons. Okay, obeying the octet rule and obeying the rules of carbon, 4 bonds, nitrogen, 3 bonds, 1 lone pair, oxygen, 2 bonds, 2 lone pairs. And if we can keep track of that, and yes, there are going to be exceptions, particularly if it's charged, but it's a really good place to start on these guys, and it's going to give you some nice structures. You know immediately that one side of this molecule doesn't look like the other. It's not all the same stuff attached. We got lone pairs on the central. This thing is polar. So again, reviewing polar, making sure that we can see our simple rules here, that if we have lone pairs on the central, or we have 2 or more different atoms attached to the central, we are going to have polarity.